Hey everyone, in this lecture we're going to be talking about population standard deviations, and we're going to be discerning the differences between population standard deviation and sample standard deviation. So let's get started. Now recall, when it comes to sample distributions, the sample averages are spread out. We can actually calculate that spread using the standard deviation. So we're going to jump over to the computer to discover the formula for the spread together. See you there. All right, so a few lectures ago, we found that there's actually this relationship between the standard deviation of my population, which by the way in this case is 11.95, the standard deviation of the sample distribution, which is 2.39, and the size of my sample, which in this case is 25. It turns out that if I take my population standard deviation, 11.95, and I divide by the square root of my sample size, which is 25, this will give me my standard deviation of the sample distribution, which is 2.39. So there is this relationship between these two numbers, the population standard deviation and the sample standard deviation. And that formula I'm going to write down over here on the left. It says that the standard deviation of the sample is always the standard deviation of the population divided by the square root of your sample size. Basically, what this says is that as n gets really big, then the blue curve becomes more skinny. And I'm going to show you guys that in a second here, but just keep in mind that this is the formula. Now, if n gets really, really big, and so in this case we have our sample standard deviation is the population standard deviation, which is 11.95 divided by the square root of n. Now I want you to take that right there, and I want you to plug in n values like 5, 10, 25, 100, 300, 1,000. The idea is as that number n gets bigger and bigger, then this corresponding quotient, the division of these two numbers, becomes a number that's really, really small, and it becomes smaller and smaller as n gets bigger and bigger. Now, why might that fact be? Well, let's talk about that for a second in this animation. Now, if I have, and I'm going to just take a normal distribution real quick. So here's a normal distribution so we can avoid the central limit theorem problems that we might encounter. So now no matter what sample size I take, the distribution should be completely normal every time. So if I take n equals 2, for example, and I take a sample. Here's my sample of 2. Here's another sample of 2. Here's another sample of 2. Here's another sample of 2. And we do this like 100,000 times. We get this bell curve right here. And I'm just going to keep doing this. All right. So let's talk about some facts about this bell curve. Number one, the bell curve is very wide. And the reason for that is because my averages are going to be pretty spread out. If I only take a sample of 2, and if I take a sample of 2 and you take a sample of 2, our averages are probably going to be different from each other. Pretty far different from each other, in fact, because a sample size of 2 is really, really low. So the spread's going to be much greater. Now, if you take a sample of like 10,000 and I take a sample of like 10,000, our averages should be closer together. So now, instead of comparing you and me, let's compare a bunch of people, like 5 samples. So here's 5 samples, and let's do another 10,000, another 100,000. Now, if you notice, this bell curve is definitely a bell curve, 100% a bell curve. And it's really, really skinny. And the reason for that is because all of my samples have are large samples. And therefore, their averages should be really close together because they're all really good samples. And so because they're all really good sample sizes, then all of the samples should be closer together. And if you notice here, the standard deviation of the population is 5, and the standard deviation is 1. The standard deviation of this skinny bell curve is 1. And by the way, 5 divided by the square root of 25 is 1. That's not by coincidence. That is intentionally mathematical in nature. So again, the idea is that this standard deviation, and I'm going to pull up my annotations real quick. I think I'm having some problems, but we can try it again. There we go. The important thing is that the sample standard deviation, which is this guy right here, is equal to the population standard deviation divided by the square root of n. So we're actually going to try this. I'm going to actually develop a random bell curve. I'm going to pick a random n, and we're going to see if this formula works. Now, this is an evidence-based proof of this formula. I actually don't know why this formula is the way it is. I have no conceptual understanding yet. Hopefully when I get that, I'll replace this lecture with a good conceptual understanding, conceptual analysis of this formula. But for now, I'm just going to verify this with evidence. I'm going to pick a random bell curve. All right, so let's do that right now. Here's my bell curve, and I'm going to clear the lower 3 so we don't get confused. I should say bell curve. I should say totally random distribution. That's a pretty random distribution right here. I like this one. There we go. It's kind of bell curve-y, but it's got some messed up parts to it. So here the standard deviation is 0.895. And I'm going to take an n of like 20, okay, which is kind of a fancier number to work with. Now I'm going to make some annotations real quick, and then we're going to get back to this animation. So I'm about to drop some like 100,000 samples on this blue bell curve, and you're going to see some like bell curve over here. But I can predict what the standard deviation of that bell curve is. In particular, if I take 8.95 and divide that by the square root of 20, which by the way is my sample size, my n, this is, according to my calculator, 8.95 divided by the square root of 20, 2, right on the nose, 2.00. So let's see whether or not this blue curve is going to have a standard deviation of 0. So I'm going to start with like 5. Now, right now the standard deviation is 1.58. Darn! Let's do another 5 though. I mean, this doesn't really look like a bell curve. So let's try it. Let's try some more. Let's add another 5. Standard deviation is 1.72. We're getting closer. Let's add another 5. Standard deviation is 1.99. That's pretty good. Let's keep going. Ah, darn, the standard deviation is 1.82 now. Let's keep adding more samples. Standard deviation is 1.94. We're getting there. Now the standard deviation is 2. Nice. Ah, now the standard deviation is 1.93. All right, let's keep going. Standard deviation is 1.86. Standard deviation is 1.84. Standard deviation is 1.8. Maybe I'm wrong, guys. I don't know. Let's see. Standard deviation is 1.83. Standard deviation is 1.78. Let's keep going. Let's keep going. I'm going to go by like 10,000 at a time. Ooh, right away, we're at 2. So 2.01, 2. Looks like we're staying at 2. And that is not coincidental. It is really intentional by mathematical reasons. Now, I don't know what those mathematical reasons are. I wish I did. Let's try one more time, one more example. I'm going to make a random distribution here. And in this case, I'm going to take a sample size of, let's say, 10. So here are my 10 items in my sample. And there's my average. And let's do like 5 of those. So right now we have a standard deviation of 8.29. Now, that's probably not the standard deviation after we simulate a bunch of these, but let's figure out what that is. So according to my formula, my standard deviation of the population is 9.85. If I take the square root, if I divide by the square root of 10, I get the number, let's see here, 9.85 divided by the square root of 10. 3.11. Now it's 3.1148, so it's kind of close to the middle, so we're probably going to notice this waiver between 3.11 and 3.12. Now right now the standard deviation is 8.29, which is pretty far. But let's see what happens to that number over time. I'm going to do another 5. 7.09. We're heading for 3.11. 6.17. 5.65. 5.14. 4.76. 4.5. 4.31. 4.29. 4.11. 4.12. 4.04. 4. 3.97. 3.86. 3.86. 3.76. 3.68. 3.69. 3.64. 3.58. 3.55, 3.56, 3.6. We're trying to get to 3.11. So let's go by, I'm just going to keep hitting the 5 button. Let's see what happens to this number. It's still going down. We're at 3.29. We're getting there. Let's keep going. Let's keep going. Let's keep going. We're at still around 3.27. We're trying to hit 3.11. We're at 3.18. We're getting there. Oh, we're back to 3.16. Excuse me. Let's keep going. 3.17. Back to 3.21. Darn. Let's see what happens here. This is really suspenseful. We're trying to get to 3.11. Will it ever get there? It's going up. Why are you going up? This is an anomaly. Let's go by 10,000 at a time, maybe. 10,000. 3.12. Eventually we'd get there. And it's wavering, you notice, between 3.12 and 3.13, which should be wavering between 3.11 and 3.12. So eventually, if I go by 100,000 at a time, yeah, you'll see it's wavering between 3.11 and 3.12. But the idea is that the standard deviation of the sample is the population standard deviation divided by the square root of 10. Let's do one more example, because it turns out that it doesn't even matter what the sample size is. The central limit theorem states that over time, the standard deviation, as your samples get bigger, the sample distribution would become more like a bell curve. But the central limit theorem says nothing about the standard deviation. So I'm going to show you guys a really quick example of using a small sample size, and this will actually still work. So here's a really random population distribution, and we're going to take sample sizes of 2. So right off the bat, that blue sample is very far from the actual true average, but we're going to do like 5 at a time. Now, before we get too far, we're going to do some math. I want to predict what the standard deviation of this sample distribution is going to be. So if I take my standard deviation of the population, 10.26, divided by the square root of 2, I get, let's see, 10.26 divided by the square root of 2, 7.25. So eventually, after this sample distribution gets a lot of data, once I put a lot of blue bricks down, my standard deviation should be close to 7.25. Now right now the standard deviation is 8.64, but it doesn't really matter. Now this is the bizarre thing. You're going to notice that this blue curve is not going to be a bell curve, and that's because of the central limit theorem, because my sample size is really small, therefore I'm probably not going to get a perfect bell curve, which is perfectly fine, but the standard deviation should still get closer and closer to 7.25. Let's see that. So I'm going to go by 5 at a time. That is a really weird curve. Let's keep going. Right now my standard deviation is 7.96, which is relatively close, but let's keep going. This isn't looking like a bell curve. That's what the central limit theorem stated, that it only will look like a bell curve as my sample sizes get closer and closer to infinity. And technically, if my population distribution was a bell curve, this would definitely be a bell curve. But that's besides the point. Regardless of what the central limit theorem says, I'm still going to get a standard deviation of 7.25, and I'm excited to see that. So let's see this standard deviation get closer and closer to that number. Right now we're at 7.45, which is really close. Kind of up there right now at 7.55, so let's keep going. We're at 7.42. We're trying to get to 7.25. 7.34. 7.32. Now we're back at 7.37, but that's okay. We're just going to keep going. So we keep adding, and this distribution looks like it's about leveling off. It's not changing much. But right now we're at about 7.37, 7.4. So the question is, if I hit the 10,000 button, is my standard deviation going to be 7.25? Let's see what it is. I'm at 7.23. Standard deviation is 7.23. That's really close. Let's keep going. Another 10,000. 7.26. 7.23, 7.22, 7.25. There we go. But maybe that's an anomaly. Let's keep going. 7.26. Ooh, I want 7.25. 7.27. Yikes. What's going on? Maybe it was an anomaly. 7.27. 7.25. There we go. Let's go by 100,000 at a time. Let's see what happens there. So if we go by 100,000, looks like it's rounding off to 7.26. Now, technically, this number here is 7.2549, which is literally 0.0001 off from rounding up to 7.26. But eventually, if I just keep going, this will go to 7.25. And I will not leave until we get there. Just kidding, we might have to leave before we get there, just for sake of time. So, unfortunately, we're a little bit off, but that could be just because we're just so incredibly close. Regardless, just understand that this formula works regardless of what your population distribution looks like. Anyways, thank you guys so much, and I'll see you in the next video. You just watched a video from More Learning. We provide free math videos, and we offer many online courses. We also provide free math tutoring via YouTube Live every Thursday and Sunday at 9 p.m. Eastern Time. Make sure to subscribe to our YouTube channel and like this video to get access to all of our free content. And put a comment in the comment section if you have any math questions. Check out all of our courses on amorelearning.org.